So Yoav is a professor at Cornell Tech University. The other big reason why he is here in Montreal is also the program chair for Column, which is happening in 3 days from now. And I'm really glad that we brought this conference to Montreal, so many of you could attend there. Coming to Yoav's research interests, see, he was also inspiration to my PhD work. Like I was doing a lot of work on language grounding using grammar and stuff like that. And Yoav's, I did use Yoav's libraries, many of those. And now he's not doing any of that anymore, including many of us. His research interests are in robotics, language grounding, and today also we're like more on the LLM side of things. This is what we'll hear from him. Thank you.
Okay, thanks, Eva. So I apologize in advance. This is not very much of an agent talk. Actually, I don't think I said the word agent a single time here. I just kind of like opted out for something recent, and I think it's pretty interesting. So hopefully it will be a fun talk, and you will forgive me for the mistopicality. Okay, so I'm going to talk about externalizing knowledge from scratch in large language models. The talk will be divided into three parts. The first one, I'll give a bit of background, very high level, talk about kind of like what happens, what people usually do when they kind of like talk about LLMs together with external knowledge. And then I'll talk about some of the safety benefit of what happens when we potentially when we separate knowledge from LLMs. And this is what's the kind of like also going to be the technical crux of this talk. I'm going to talk about something called limited memory language models. It's kind of a new paradigm to pre-train LLMs. We call it LLMs. And I want to kind of like already here give the credit to this very large team that put this work together, especially Lindsay Zhao, the student who led this, and my colleagues Jennifer and Killian. Okay, so LLMs, they're trained to be very knowledge rich. There is actually no sense of separation between knowledge and skills, either linguistics or reasoning in LLMs. And this simplicity and this lack of abstraction is partially why they are so successful and scalable. There is this notion of using external knowledge LLMs that usually does in the sense of augmentation. We're going to improve the LLM by giving it more knowledge. And this is done usually kind of like two dominant paradigms, retrieval augmented generation or RAG or tool use. And the boundaries between these two are becoming very vague. So RAG's kind of like the whole point in RAG is we want to give the model more knowledge, because what we want to do is we either want to edit knowledge that it doesn't have access to, or we want to emphasize knowledge that maybe it's so in pre-training, but it's going to be very relevant to the task. It was introduced by Louis in 2020. They had this really cool but fairly complex way to do it. They had this end-to-end post-training approach. I kind of like forgot about it because I used to think about RAG the way we think about it today, but they basically post-trained the whole thing end-to-end, the generator, the retriever, the query encoder, and they had this like really cool way of doing latent variable for the document selection. So very interesting, very cool. This is not at all how RAG is used nowadays. The techniques are much simpler, but it's really all over the place. Today, RAG is kind of like looks more like a tool use. And the goal in tool use is we're going to fine-tune, or we're going to prompt a model, so we're going to call some tools. And this is something that happens in agents all over the place. You get this like really nice, simple kind of like process where the model generates a function call, just kind of like generates a token. Then it's very easy to identify, so you stop the generation externally, you execute the call, get whatever the return value, make sure it's in some kind of a text form, unless you're in multimodal land, and then you force encode them through the LLM, and you continue generation conditioned on that. And the kind of like the quintessential paper in the space is Toolformer. The whole point is they post-train LLMs to use various tools, and their goal is really performance boost. And they have these like really nice figures that illustrate how effective it is. Blue line with tools, red line without tools. The gap is big, the approach works great, and it's a kind of cross-model scales. The key to their approach is this really kind of like nice pre-processing step. So they are going to take regular language model data, which is a fancy way to say raw text, and then they're going to have this like pipeline process where they sample API calls, execute them, filter them, and so forth. And at the end, they get what we see there on the right. They get these text, but now it has in the middle these like API calls and their return values. Then they take this text and they just do next token prediction on it. So they just kind of like use it as a post-training, but just simple SFT. And interestingly enough, and that's something kind of like it's a small detail, but keep it in mind because we'll get back to it. They compute loss on all the tokens, even the tokens that the LLM will never generate because they are returned by the tools. They just went for the simplest approach. Okay? So RAG and tool use, they are really about performance, adding or emphasizing knowledge. Externalizing is going to be a very different game. What we want to do is we want to tease out the knowledge out of the model. So it's not stored in the parameters anymore. And this, I would argue, has some very significant benefit along like many dimensions, but specifically along scale and control dimensions as far as safety and risk. So let's talk about scale. So scale is everywhere. That's the main avenue that drives development for the last few years. Basically, the mantra is, if you wanted to perform better, just make it bigger. And also, as a result, a significant focus of regulation. So US regulation, although it's changed the shift in the administration, and the EU's AI Act, they both define scale reporting thresholds. There is this belief that once you reach a certain scale, certain behaviors become more likely or and certain potentially undesired behaviors. But despite this reporting requirements, subscribing to scaling as like the avenue forward carries like really meaningful risks. And that includes to privacy and autonomy and around energy consumption. So dependence on large models basically tethers you to data centers. So you're really dependent on externalizing your compute. And this externalization, this processing is not going to be encrypted. So the model providers, they basically see all your data. And this is not only about selling data for them or just accumulating it. So it's not about being kind of like greedy about data. They actually provide very useful features. So they memorize between interactions, and they can really adapt to the user. There's a lot of interesting stuff happening under the hood. But this kind of externalization is really compounded by current trends in how we develop LLMs. We're exposing more and more data. And there is this like really big trend. We are switching from push to always on models. So models that are kind of like ambient, observe everything that's happening on your computer or have access to everything, just like the computer use agents that people talked about today in various talks. There are AI glasses that are kind of like observing everything that you are seeing throughout the day and just streaming it to the servers. So, and et cetera. So there is this like trend where more and more data, people are handing more and more data to the model providers so they can compute and reason about it. And this combines with another feature of LLMs. They're really good at analyzing data and text. So now we can apply this personal treatment at scale, right? It used to be that if we have very large data at a very large scale, all we can do is just like very high-level statistical analysis. But now if you want to identify an individual with a specific behavior out of like a very large population, you can do it. So being a part of a large crowd no longer provides anonymity or any sense of like privacy. For hackers on that, so everybody that wants access to this data, is the companies or even the governments that can subpoena this kind of data can get it. It's also a really nice kind of like honeypot for hackers, except that there are no bees. If they hack inside, they can get all this data, and they can get it by hacking into a single kind of like location. So one lock keeps a lot of value. Now you can always argue, like in many cases, when you talk about kind of like tools that use a lot of data, that you can opt out. But this is becoming actually increasingly difficult because if we buy the kind of like argument that these models have a lot of value, that they're very high capability, and I think people in the language modeling world subscribe to this approach, to this attitude, then opting out of using them carries like increasing costs. So you're actually putting yourself at a significant disadvantage if you're like, I'm just gonna, I'm gonna stay in the 2010s. So privacy and autonomy at the bottom line, they just really require you to do your own compute. Ideally end-to-end encrypted. And this does not work at all with scaling trends. Now there is an aside to this, this is just to to point out, this is actually part of a much larger discussion about LLMs and democratic values, and I recommend, in the context of agent, I recommend this manuscript. This is also part of a larger series of articles about this topic, where from the Knight's First Amendment Institute in Columbia, and so this is linked from here. Another risk of skill is energy consumption. So we are seeing these headlines about companies reopening old power plants and even nuclear power plants with some very miserable histories, like the 3 Mile Island. The US energy demand for the first time increased and for the first time in 2 decades. So there is a serious problem with what the energy consumption that we are creating with these models. Now, of course, there is a lot of work on increasing efficiency, and this is great. This is orthogonal to just making the models smaller, so you can benefit from both of them. So externalizing knowledge has this it's very it's a promising area to to make models smaller, because there is this really strong relations that we get from scaling laws between tokens, compute, and parameters. So we have this really nice avenue to ameliorate a lot of the risks of scale. Another issue with very knowledge-rich models is they're very opaque, and that provides very little control on the kind of knowledge they have, or the kind of knowledge they produce or they use to make certain deductions. And controlling this is actually a really big challenge that is an open problem. Unlearning, it's extremely hard to address. It's also very hard to evaluate. Every time a benchmark comes, it seems like a few months later, there is the paper that shows why it's not as effective. This is a very interesting paper that is coming up in Cologne later in the week. There is factuality and hallucinations. Even now, they remain a big problem, especially in more complex niche topics. And then there is consideration of using undesired, high-risk, or proprietary knowledge. So externalizing knowledge, if you remove it outside the model, it gives you this really nice place to control what models the data is using. Okay. So this is motivated us to look at what happens how can we limit the kind of knowledge that language models have, and for that we designed LLMs, limited memory language models. The research question there is, can factual memorization be disentangled from language and reasoning proficiency in language models? So the vision is, and I'm definitely not going to deliver on it, so don't hold me for it, is that knowledge is a fully modular, controllable thing from the onset. So this is not about post-training. We know that post-training is very powerful, but it's a very shallow and brittle treatment. This is really from the get-go, from when we start training the model. And that means the data can be added, deleted, access controlled. Models remain extremely capable linguistic and multimodal reasoners, but they are not maximal knowledge repositories. So this is the big distinction. And that's where it really differs from RAG or tool use, because the goal is not to maximize access to knowledge. The goal is to minimize the internal knowledge. Okay. So LLMs relies on this very wishy-washy distinction between 2 types of knowledge. And there is no clear definition here. I'm just going to show it with examples. On the one hand, we have common knowledge, and on the other hand, we have specific knowledge. Common knowledge is going to be this general information that is broadly applicable, for example, to many, many entities. So, for example, Napoleon was a person, he has a mother, she gave birth to him, and it happened somewhere, sometime. On the other hand, more specific knowledge is much more tail knowledge, harder to compress, much more specific. So Napoleon was born on August 15, 1769. He was born in Ajaccio, Corsica, and I apologize if I'm butchering the pronunciation. And his mother's name is Letizia Bonaparte. Okay? Now, what do LLMs learn? Well, just about everything, right? They get language competency, They get this factual knowledge that Napoleon is a person and he has a mother, but they also get all this tail knowledge. Napoleon was born on a very specific date, in a very specific time. His mother's name was Letizia Bonaparte, right? What we want to do is we want to take that last part there on the right and we want to switch it into an external database so it doesn't go into the model parameters. So what does it give us? It gives us models that are hopefully faster to train. They're smaller in the sense that they give you performance that is equal to much larger models than they are, if you kind of like compare across scales. And that means that they are going to be cheaper to train and deploy. On the other hand, they will be augmented with a very large database, but that database will be interpretable, editable, and linked to sources. So all the kind of like nice stuff we want kind of like knowledge to have. The methodology of LLM is actually pretty straightforward. So it takes a node, kind of like a page from Toolformer, and it has this like, and in the pre-training stage, has this like, we do two parts. We create a database and we estimate weights. But the crux of the process is pre-processing of the pre-training data, of the raw text we use. In inference, very straightforward. We generate retrieval queries and get return entities, so it's just like tool use. So it's really kind of like stitching together techniques that are very common, putting it just in the right way. Okay, so how do we do data processing? So what we want to do, we want to identify contiguous strings that represent tail knowledge, and we want to replace them with database query calls. So if like we have this sentence about Napoleon, we want to identify the date of birth, the location, and the name of the mother, and we want to process this text into this one. And you can actually see that, you see it looks very much like a kind of like tool calling augmented text. Now we have all these database queries where they have an entity and a relation in the arguments, and what we return is the value that we would like to generate later. So kind of like the values that are in blue that you wanted to tease apart. Okay? Okay, so how do we do that? It's a very simple pre-processing pipeline. We use GPT-4o, and a relatively expensive large model, to annotate about 1,000 documents using a prompt. So it's like a prompting technique. We wanted to extract factual entities and create this initial seed data. We showed some examples, so there's a notion of in-context learning here. We get 1,000 documents annotated like this, and then we filter them, because this annotation is actually going to be somewhat noisy in some kind of like nasty ways. To filter it, we train a corrector model. The way we do that is we take a smaller model, an 8B llama model, and we train it just a bit, so it underfits the data. And that means it will assign a high loss to bad example, which is harder to fit. So we filter out the top 10% by the loss. What do we remove? We get rid of contextually unsupported examples. So these are examples that kind of like refer to text that appears after the query. So that happens sometimes because GPT-4o sees the entire text, but it doesn't really support autoregressive generation. We remove some overly specific stuff and some ill-formed queries. Then we take our cleaned up data and we just SFT another Llama 8B model as an annotator model, and we run it kind of like a forward pass to annotate our entire pre-training data. Okay? So now we have pre-training data that is annotated with these queries. Okay, so we pre-process the data. Now we have to get this database. That's really simple. We just pull all the tuples from our annotated pre-training data. And a tuple looks like this. It has the arguments to the function, Napoleon and birth date, for example, and the return value. So we have this like triplets, and we just throw them all into a database. There is a very, very little normalization happening here. Generally, these are just strings. So there is no kind of like canonicalized ontology that works in any particular way. There's just a bit in the prompt, but nothing really standard. Okay, so we have the database. We have our pre-processed pre-training data. Now we are going to kind of like pre-train LLM. We're using the conventional negative log likelihood loss with one difference. And this is where we depart from toolformer, and this is really important. We exclude tokens of the DB return values. So we simply don't compute loss on them. We have this indicator function. It's a very straightforward combination. So the text with the gray background is not up. There's no loss on it. Everything else has loss values in it, including the blue kind of like parts, which we want to externalize. What happens here is we're really relying on kind of like this Occam's razor property of training large models, that they look for the simplest solution. What is the simplest solution to generate August 15, 1769? Just copy it from from the return value before. And transformers are really good at copying. So it relies on this kind of like property of them. Now, unlike transformer, and this is really critical to externalizing, we're not computing the loss on these gray parts. So it's really learns it doesn't really optimize on this knowledge. Okay, inference is super straightforward. We do conventional text generation with tool calling. We have this special DB function that the model is trying to generate. The return values are encoded into the model, and generation continues. There's one kind of like small caveat. Our database is not standard in any way. So we have a key matching problem. We solve it in a very kind of like hacky, simple way. We just use fuzzy matching using a string distance. We embed and just get the tuples that is close to it. If the distance is under a certain threshold, that we tune on a validation set. Okay, it has certain advantages. It allows us for misses if nothing is in the area where we land, but it's hard to recover from errors. It has a large memory requirement, so it works, but it's kind of a hack. Okay, for experiments, sorry, I have a typo there. Okay, so let's see what this can do. So we take Wikipedia corpus of 3 billion tokens, we pre-process it, and then we get almost 55 million knowledge triplets from it. This is our database. We experiment with two knowledge architectures, GPT-2 and Llama 2, and for both of them we try two sizes, 124 and 355 for GPT-2. This is like small and medium, and Llama 2, 176 and 382. Like tiny and less tiny. Basically, both of these architectures, given the size of our pre-training corpus, they're all going to be under-trained. So we iterate multiple epochs over the data. Okay, first thing, perplexity, because we are in pre-training. Okay, so what do we see here? So we see the four models, and for each of them we see several perplexity values. The top one, the lightest blue, is the standard perplexity. What happens if you just optimize over the data, like a very standard a pre-training objective that gives you some kind of like a frame of reference. The second one from the top in each of the clusters is dynamic. Dynamic is the lam perplexity if what you're doing is you're actually generating the queries and you get the return values from the database. So this is kind of like comes to give you the real-life perplexity. And you don't compute perplexity on the queries itself and their return values. And you already see a significant decrease in perplexity, basically telling you how the Lambda models can kind of like fit the data and generalize much better. This is validation data, of course. The third one, the normalized, this force encodes the gold queries, not the gold return values, and for them, and computes perplexity over the queries themselves, but not over the return values. And you can see that it's relatively low. What it tells you is that generating the queries is not kind of like a very hard task. So you can do it fairly well, much better than just kind of like memorizing the facts. And the oracle is oracle. It's like everything is gold. So we have like really nice perplexity at the end of training, significantly better than what we get from kind of like a vanilla pre-training. We also have very nice training trends, right? We expect, because we're asking the model to do much less, you don't need to memorize all these facts, we would expect it to learn much faster. And indeed, that is what you see. So here you're seeing normalized perplexity on the Llama 2 architecture, on the held out set throughout the learning. So you have pre-training tokens at the x-axis. And what you're seeing that for both sides of the models, the perplexity trends are much, much better. They're throughout, they are much lower than with vanilla training. Another thing we get from LLM is a much better factuality capability trade-off. So what we're seeing here on the y-axis is fact score. That's kind of like a measure of factuality. And on the x-axis, you see NLU average performance. So the number of tasks here that we use to kind of like as proxy for general capabilities. So you can see all the kind of like pre-trained models. They have this like really nice kind of like scaling curves. Performance and factuality go up. These models are, by the way, generally trained on much larger data sets than our LLM model. LLM provides kind of like similar performance as far as like utility. This is the NLU average performance to other models at its size. But it's really kind of like, gets away from the pack along factuality. So at this level, it gives you factuality scores that are much higher. These factuality scores are comparable to a 7 billion model. And we get them with a 176 or 382 million parameters model. Okay. Another thing is like we talked about control. So just kind of like, so really when you start thinking about unlearning in LLM, it becomes much kind of like simpler. All you need to do is kind of like operate on the external database and remove and add facts as you see fit. So this is evaluating on the TOEFL benchmark, and the TOEFL benchmark has this like really nice kind of like trade-off between unlearning steps and forget quality and model utility. And this is the NPO method, but usually what you see is like, you optimize more, you forget better, but you have some kind of like weird behaviors as far as utility, and after a while, the model is useless. But with LLM, there is no unlearning step. You're just discrete operations on the database. So we have this like really nice straight line with basically very nice forget quality once we start removing things, but keeping exactly the same utility. So again, because we externalize to a database, there is this really nice way to intervene to control the data. Just kind of like a bit of an ablation. So when you remove the database, LLM is not great. So that kind of like shows you that it's actually not memorizing. It really relies on the database. So this is when you compare the gray bar and the green one. And this is like two measures of factuality. Another interesting thing is what happens to the training loss when you look at like tokens during training. So if you just take LLM data and you SFT it, just the regular data, then you will see the loss on the query returns decreasing over time. That's as expected. That's kind of like you're fitting the data. But because LLM does not, in LLM process, you don't optimize over these tokens, what you see is actually the exactly reverse trend. The loss on these tokens is increasing. So you're not, and that tells you that you're not memorizing these facts that are returned. And that's why it's critical not to compute the loss values on the return values. Okay, so let me kind of like summarize because some kind of like the open question is limitation. So I think, we have this like a relatively different pre-training approach, but it does have a lot of limitation and it leaves a lot of open questions, which I think makes for a lot of interesting research in the future. So first of all, we did it with Wikipedia data, and which really simplified a lot of problems because it's very fact-rich. It's not completely clear how to apply this approach to non-Wikipedia data, like think about archive articles or a newswire text. It's also not clear how to scale this up to real-life pre-training scales. I mean, I think technically it's not that difficult to expect another forward pass with a smaller model on each piece of text you're optimizing on, but it still adds a significant cost. We used only 3 billion tokens as our pre-training corpus. I told you that for query matching, we did this fuzzy matching with the threshold. It feels very unsatisfying and pretty brittle because there is a clear threshold there. There were very difficult kind of like interesting questions about what about more complex inference. So what would be the LLM query for continuing the sentence? The list of ML researchers teaching at Cornell includes so and so and so. Just getting a single tuple doesn't give you the information that allows you to continue this kind of generation. And finally, this connects to it, is there's this question of the rigidity of tuple representation is limiting or not. My kind of like personal hypothesis, it is very limiting. Okay, so to summarize, LLM is a pre-training approach to externalize knowledge. It builds on existing techniques in a RAG and tool use. But these kind of models, they combine them in a very different way to provide several really promising properties. So we have a fast training, increased factuality, and better knowledge control. And it points forward to this development of models that are very strong reasoners, but actually don't hold all the knowledge. So kind of like the analogy all of a sudden is that the model is not just this all-capable monolithic machine, but almost like a librarian that can sit in a library, and whenever you ask a question, they will go and get the right book and kind of like give you a very quick answer. Okay, so thank you very much. If there is time, I can answer a few questions, but I don't want to stand between you and the reception.
Thank you very much. You have a very interesting project. So you made just this analogy of a librarian, right, who can fetch relevant things. But we want also models to be kind of scientists and learn some more general, right, abstractions. And I'm wondering, by kind of removing this detailed factual information, maybe you limit what they can actually learn about this data. But maybe specifically when we talk about named entities and triples, in Wikipedia, I'm not sure, it's a bit hard to make a good example, but if you start removing, for example, archive papers and forcing it to forget, you know, important details in these papers, how would it learn how to produce new methods, right?
Yeah, so I think the answer for that is like, so first of all, I don't think the current formulation handles this well, because the tuples are not really sufficient for this kind of reasoning, and retrieving a single tuple for a fact is just not enough to give you an answer. But you can think about kind of like where you can develop this approach. So maybe it's not tuples anymore. Maybe it's more complex representation. Maybe you can do more manipulations on them. Maybe you have a really, really long context and you're doing reasoning. So suddenly, like, you can think about kind of like a model that is accessing all this knowledge, synthesizing it on the fly in context, and kind of like building on top of it, and building the abstraction as it does the inference, rather than try to bake it into the parameters. What we find when we look at like so when I try to do stuff on archive papers with state-of-the-art frontier models, like ChatGPT or Claude, I usually find a pretty miserable experience. There is a lot of hallucinations. I mean, and I really like it when it kind of like hallucinates papers and then kind of like create these Frankenstein researchers by combining names of, like, you know, Siva Choi wrote this paper or something. And I get this all the time. And so it's just, you know, I don't think the models are actually even doing better on this kind of domains. But you're right, there is a challenge, and this formulation doesn't apply kind of like straight away.
Yeah. So I think maybe just to crystallize it a little bit, my worry is that you're not making the model predict some kind of very fine-grained information, and by kind of not making it to predict this, right, maybe you are not forcing to learn some complex kind of derivations internally.
Yeah, so that's an interesting thing, because so we're not making it predict the facts, but that's where the copying is. But it will have to use this information to predict follow-up queries, because there are because you can think about LLM as kind of like you know, like RAG on amphetamines, right? Instead of like having one RAG per query, you have that almost every few tokens. So the reasoning to predict later tokens actually requires that. So there is still a lot of like complex reasoning happening there, and it's pretty challenging during pre-training. But you're right, at the end of the day, it's an empirical question, and we didn't try it on these kind of complex domains.
Okay, just one final question. Thank you, Professor, for the presentation. I was wondering what was the main reason for generating your triplets from data from Wikipedia instead of using already existing knowledge base like DBpedia?
So I think it's the answer. I mean, the Wikipedia source just simplifies a lot of things. It allows kind of like, because Wikipedia is really, it's kind of like, what is it? It's an encyclopedia. It's basically a list of facts kind of like composed into a text. So if you want to get like factual tuples, it's a really good and easy place to start. So you can almost think about it as a simplifying assumption. And that's why, as Ivan points out, there is this like really hard kind of like research problem now of how to take this and extend it to other domains, like archive or literature or newswire. But so the Wikipedia is very much like just an easy, comfortable place to start.
Thank you. All right, yeah, the social starts now, and thanks.
Thank you.